Hello and welcome back. We are now on chapter 17 of Materials Kinetics, which is non-equilibrium viscosity and the glass transition. I would like to start in someplace really pleasant here. How about Paris and the Sainte-Chapelle stained glass windows there? This is a beautiful work of art where if you go inside, you're just surrounded by these very tall stained glass windows, each one of them telling a detailed picture from one story of the Bible. And it's like being inside this just beautiful work of art. But the reason that I'm starting with this particular slide is that if you look really closely at the individual pieces of stained glass in this or in many different medieval cathedrals, what you might see is that the glass appears to be a little bit thicker at the bottom compared to the top. And this has led to an urban legend around the world where people believe that the glass is actually flowing over time, over the centuries. So these particular stained glass windows are about 900 years old, and people believe that that is enough time for that glass to be very slowly flowing, becoming thicker at the bottom compared to the top. Now, this is an urban legend that was, uh, discovered or learned by one of my good friends who's a professor in Brazil, Professor Edgar Zanotto. And he thought at first that it was just a kind of a local legend within Brazil and was surprised to learn that many of his colleagues from Europe and from North America had also heard similar stories. And so he did an investigation into this question, do cathedral glasses flow? And published an article on it in the American Journal of Physics in 1998 that got a lot of attention. And what he did was he used the viscosity curves from some modern glasses and then used this equation that we learned last time, the Vogel-Fulcher-Tammany equation, which describes the temperature dependence of the viscosity of liquids and supercooled liquids. He used this equation and extrapolated down to room temperature and estimated that the glass would flow, but it would only flow on the time scale of about 10 to the 33 years. So many, many orders of magnitude older than the cathedral and, of course, much older than the age of the universe itself. So his conclusion was that that's not nearly enough time for the glass to be visually flowing for the cathedral glass, and basically that the thickness variations are just a byproduct of the medieval manufacturing process, which couldn't ensure thickness uniformity, and then it was only natural for the stained glass artisan to put the thicker part of the glass on the bottom because it had at least the appearance of being more mechanically stable. So that paper got a lot of attention, but there was one reader who kind of questioned one of the assumptions that was made there, and that was another good friend of mine, Professor Prabhat Gupta from Ohio State University. And together, Zanotto and Gupta published this follow-up paper in the American Journal of Physics in 1999, where they argued that that Vogel-Fulcher-Tammany equation really is only meant to describe the temperature dependence of the viscosity of the equilibrium liquid phase. In reality, though, that supercooled liquid would freeze into the glassy state at viscosities around 10 to the 12 Pascal seconds, the glass transition temperature. And within the glassy state, the temperature dependence of viscosity would be more Arrhenius, or the so-called isostructural viscosity that corresponds to the frozen-in structure of the glass. And that this viscosity of the glassy state would be orders of magnitude less than the viscosity of the liquid. And they used estimates of the non-equilibrium viscosity of glass at room temperature based on modern soda-lime silicate glass, in other words, a modern formulation of window glass, and came up with this new estimate that the glass would flow, but only on the timescale of 10 to the 23 years. So the fact that this was so many orders of magnitude less tells us the importance of accounting for thermal history and accounting for the non-equilibrium viscosity of the glass and not assuming that it's the same thing as the liquid. even though this new estimate was many orders of magnitude less than the original estimate from Zenotto. Note that it's still much longer than the age of the universe, and still the overall conclusion that the cathedral glass is not flowing is still valid. The reality is that if you go back to how this glass was made in medieval times, it was made by putting a gob of glass at the end of this rod here, spinning it out, and then the centrifugal force basically pulls it out into a disc. And of course, in the middle, it is naturally thicker compared to the outside part. And then the artisan would cut this up into different pieces that would be used for the stained glass windows. So there would be natural thickness variations because they didn't have modern technology back then to ensure uniform thickness. And it's just natural then for the stained glass artisan to put the thicker part at the bottom. So it's just a byproduct of this medieval manufacturing process, but it is telling us a really important lesson here, and that is that we need to account for the thermal history of the glass to determine its non-equilibrium properties, including the non-equilibrium viscosity of the glass. And this really goes back to where a glass comes from and what is the glass transition itself. We can learn about that from this figure, which is called the volume temperature diagram. And this tells us how we get a glass, and it points to some of the important underlying physics of the glassy state. So let's start up here at this point A. This is at high temperatures here and high volumes. You'll see the temperatures on the x-axis. Volume or molar volume is here on the y-axis. And if you take this high temperature liquid and cool it down, the liquid will contract to point B. The slope of this line here will give you, it's related to the thermal expansion coefficient of the liquid. Now, what normally happens, as we learned in our lecture on nucleation and crystallization, is that if you get a little bit below the melting temperature of the liquid, that's when you've got a thermodynamic driving force for crystallization to happen, and also the kinetics are fast enough to actually observe crystallization. So at this point C, a little bit below the melting point, this is where the liquid, if it were to stay in equilibrium, would crystallize. And this crystallization involves having this discontinuous change here in molar volume, enthalpy, entropy, coming down to this crystal line here, and then continued cooling of the crystal would lead to the crystal contracting according to the crystal's thermal expansion coefficient until you get down to this point E. So this is what happens at equilibrium. However, crystallization takes time. As we learned in our lecture on nucleation and crystallization, it takes time for the atoms in the liquid state that are disordered to rearrange themselves into an ordered crystalline configuration. And what if that cooling process is so fast that we simply don't allow the atoms enough time to be able to rearrange themselves into an ordered crystalline configuration? In that case, we get what's called a supercooled liquid. A supercooled liquid is any liquid that is cooled below its normal freezing point. The supercooled liquid is not the thermodynamic equilibrium. It is what is called a metastable equilibrium, meaning that there is a lower free energy phase available, which is the crystal phase, but it takes a phase transition in order to get that. So the supercooled liquid, if you just leave it alone, would be stable, but in the limit of very long time and when it's exposed to various thermal perturbations, over time it will undergo a phase change and crystallize. Now, as we have this supercooled liquid, as it continues to cool, the viscosity of that supercooled liquid continues to increase, and it increases by orders of magnitude, as we learned in the previous chapter. At some point, which is around a viscosity of 10 to the 12 Pascal seconds, the flow behavior of the supercooled liquid becomes rather slow. It becomes on the same timescale as a typical experimental observational timescale. And when you have continued cooling after that, the viscosity continues to increase by orders of magnitude And eventually, the time scale that it takes for the supercooled liquid to relax becomes longer than the time scale that we have to observe it. And when that happens, this is what's called the glass transition or the glass transformation. Now, this is not a phase transition that occurs at a particular temperature. Rather, this is a kinetic transition that represents a gradual freezing in of the supercooled liquid structure, as it just simply takes too much time to be able to have configurational changes in that liquid. And with that gradual glass transformation process or glass transition process, we get a gradual freezing in of this disordered supercooled liquid structure into the glassy state. And then, as we continue to cool that, then the glass will contract according to its own thermal expansion coefficient. So the glass itself is a material that behaves a lot like a solid in terms of its mechanical properties, but its structure is very similar to that of its parent supercooled liquid. And the key thing is that the glass transition itself is not a thermodynamic phase transition. It is a kinetic transition because we are imposing some time constraint on the system. We're observing it on a time scale that is too fast for it to achieve its equilibrium. Now, glass is not the equilibrium state, and it's not even a metastable equilibrium state like the supercooled liquid. Glass is unstable. It is out of equilibrium or a non-equilibrium state. And this glass is continually relaxing towards the supercooled liquid, which in turn is metastable with respect to the crystal. And the key thing is that it doesn't require a phase transition for the glass to relax towards the supercooled liquid. The glass is continuously connected to the supercooled liquid state, and over time, it's gradually approaching the supercooled liquid state. And the kinetics of that relaxation process, the process by which the glass continuously converts towards the supercooled liquid state, that accelerates when you increase the temperature of the system. So if you take this glass, heat it up close to, say, the strain point or the glass transition temperature, then you can actually observe this relaxation happening in real time as it approaches the metastable supercooled liquid state. But one of the key byproducts of glass being a non-equilibrium state is that the properties depend not just on the chemistry of the glass and the current temperature and pressure, but they depend on the entire thermal history and also the pressure history of the system. For example, here you see two different lines that correspond to a fast-cooled glass, which has a higher molar volume compared to the slow-cooled glass, which has a lower molar volume. With the fast-cooled glass, if you follow this back up to the supercooled liquid state, what you see is that the fast-cooled glass has a glass transition that occurs at a higher temperature compared to the slower cooled glass. And that's because with the fast-cooled system, we're giving the supercooled liquid less time to stay in its metastable equilibrium because we're cooling it down too quickly. And therefore, that forces a glass transition to occur at higher temperatures. With the slowly cooled glass, in this case, since we cooled it more slowly, we're giving the system more time to stay in its metastable supercooled liquid equilibrium before it's able to depart from that equilibrium and become a glass. So slow cooling corresponds to spending more time at each temperature. Therefore, it's able to follow the supercooled liquid line down to a lower temperature before finally undergoing the glass transition. So the properties of the glass depend on its thermal history. It's actually a rather complicated function of thermal history, but one kind of the simplest way to represent that thermal history is using a concept called the fictive temperature. And the fictive temperature is one way of getting that is by taking this glassy line here and drawing the tangent line to it and see where it intersects the supercooled liquid line. The temperature at where it intersects is denoted TF, and that corresponds approximately to where the supercooled liquid is frozen into the glassy state. In reality, that freezing in process occurs over a broad range of temperatures, but the fictive temperature is kind of an approximation of where that supercooled liquid is freezing in. You'll see for the slow-cooled glass here that the fictive temperature is relatively low because the structure of the slow-cooled glass corresponds more closely to the structure of the supercooled liquid at lower temperatures. However, if we were to take this fast-cooled glass here, draw the tangent line to this fast-cooled glass curve, and see where that intersects the supercooled liquid, when we drop that down to the temperature axis, that has a much higher fictive temperature because the faster cooling gives the supercooled liquid less time to stay in equilibrium, and therefore it falls out of equilibrium at higher temperatures. So the structure of the fast-cooled glass is a more open structure that corresponds more closely to the higher temperature supercooled liquid. So this fictive temperature is like an additional thermodynamic order parameter. It's an additional parameter that tells us more information about the thermal history of the glass, so that when we determine the properties of the glass, whether it's molar volume or enthalpy, or in the case of this lecture, the viscosity, that is that additional piece of information that we need to describe the thermal history dependence of glass properties. So the key takeaways are that the properties of a glass, because it's a non-equilibrium system, depends on both composition and thermal history. Glasses have non-equilibrium property values that continually relax towards the metastable equilibrium of the supercooled liquid state, and the non-equilibrium state of a glass is commonly described in terms of its fictive temperature. Now, recall from last time, one of the key concepts with the viscosity of liquids is Angel's concept of strong versus fragile liquids. And this is just in the liquid state. So note the temperature axis here, Tg over T. The 0 here is infinite temperature, so it starts at the limit of very high temperature, and then it goes down to Tg over T equals 1, which is the glass transition temperature, defined as being the temperature at which the supercooled liquid has a viscosity of 10 to the 12 Pascal seconds. So all of these viscosity curves for all these different chemistries, they're all passing through the same point here, 10 to the 12 Pascal seconds, at the glass transition temperature, because by definition here, the glass transition is occurring at a viscosity of 10 to the 12 Pascal seconds. And what Angel observed was that there was a couple of liquids here that had this Arrhenius scaling of viscosity with temperature. He called them strong liquids, presumably because the structure of those liquids is not changing appreciably as a function of temperature, whereas most of these liquids here exhibited some departure from Arrhenius scaling, and he called these fragile liquids and quantified that degree of fragility with the fragility index here, lowercase m, which is simply defined as the slope of this curve at the glass transition temperature. So it's the slope of the base 10 logarithm of viscosity with respect to Tg over T evaluated at the glass transition temperature. And therefore, a higher fragility index indicates a steeper slope. And because of this common intersection point in the infinite temperature limit, that also means that there has to be a greater curvature here, so a greater degree of non-Arrhenius scaling. Now, Angel's plot here has a lot of great physical insights, and what we will see is that the fragility of a system also has a big impact on the non-equilibrium viscosity of the glassy state. But this plot itself only dealt with the liquid state. If we were to go onto the right-hand side of this plot, that would be cooling to temperatures below the glass transition temperature, where we're falling out of equilibrium. And so at those temperatures to the right of this plot, we would need to account for the thermal history of the system. Recall also from last time that we considered a number of different models for the temperature dependence of liquid viscosity. And the most accurate of these was this Maega equation. The Maega equation has 3 parameters, which is this eta infinity, the extrapolated infinite temperature of viscosity, which is a universal constant, and then 2 unknown parameters here, K and C. And the advantage of this compared to, say, the Vogel-Fulcher-Tammany equation is that it bypasses the problem of dynamic divergence. The VFT equation was predicting infinite viscosity at a finite temperature, which is unphysical. The Maega equation bypasses that problem and gives a more accurate description of the experimentally measured viscosity data. So if we take this Maega description of the equilibrium viscosity of some liquid and supercooled liquid system, in this case, this is for Corning Eagle XG glass. This is the glass that is on most televisions and computer displays. This shows the base 10 logarithm of viscosity versus Tg over T. And this region of the curve here from 0 to 1, this goes from infinite temperature to the glass transition temperature. If you draw a box here, this would be the Angel curve within this box from 0 to 1, going up to 10 to the 12 Pascal seconds. Now, what happens if we continue to extrapolate the Maega equation is that this blue curve continues to increase in a non-Arrhenius fashion, and this corresponds to the equilibrium viscosity of the supercooled liquid. And you can see that this gets to very high values of viscosity. You see 10 to the 28, 10 to the 32 Pascal seconds. That is if you somehow manage to stay in the supercooled liquid state. In reality, because of the timescale constraints that we're on, there's going to be a falling out of equilibrium. And when that happens, the supercooled liquid undergoes the glass transition, falls out of equilibrium. This is a gradual process here, and then eventually freezes into the glassy state when the glass is basically frozen in on the timescale of interest. That's when this viscosity curve becomes Arrhenius. This is the isostructural viscosity, meaning the constant structure viscosity. If you cool the system quickly, you'll end up with a higher fictive temperature. So this green curve here shows a fictive temperature of 760 degrees Celsius. This corresponds to a fast-cooled system. If you take the same supercooled liquid and cool it more slowly, you'll end up with a lower fictive temperature, which in this case is 720 degrees Celsius. And already you can see that there is a difference of the viscosities of this non-equilibrium system just based on the thermal histories. So if you take a vertical slice through this plot, that would all be the same temperature. But you see these two different glasses here that have two different thermal histories. Even though they're both the same chemistry and at the same temperature, the viscosity is changing by more than an order of magnitude here. So it's actually a huge change of viscosity just based on the thermal history difference, depending upon whether it was cooled quickly or cooled slowly. And what's even more is if you were to take that vertical line and go all the way up to the liquid state, you'll see that the liquid viscosity is many, many orders of magnitude greater than that of the glassy state. And this is a little bit counterintuitive because if you're in this low temperature regime and you ask which system is flowing faster, the liquid or the glass, the fact is that the glass is actually flowing a lot faster than the liquid because the glass has a viscosity that is orders of magnitude lower than that of the liquid. Of course, in practice, if you're at very low temperatures, all of these systems have very high viscosities. And so the flow behavior of any of them is going to be very slow, oftentimes too slow to observe. So how do we describe mathematically this non-equilibrium viscosity of glass? The equation that describes this is this Mauro-Allan-Potuzak or MAP model of the non-equilibrium viscosity. And this is derived from the Maega equation. The Maega equation is giving the viscosity of the liquid and supercooled liquid states in equilibrium and metastable equilibrium. And it is based on the Adam-Gibbs equation, which is relating the viscosity back to the configurational entropy of the system. Now, if you assume that the structure of the glass corresponds to the structure of the supercooled liquid frozen in at the fictive temperature Tf, that's like freezing in a particular environment around the glassy state, which gives you a particular number of possibilities for viscous flow. And so with that kind of frozen in local environment, we can derive a new equation that accounts for the thermal history dependence of the glass viscosity. And the final equation that we end up with has two parts to it. So this is the base 10 logarithm of the non-equilibrium viscosity of the glass, which is now a function of the temperature T, the composition X, and the fictive temperature TF. So we've got this additional fictive temperature dependence in here. The first two terms here are a constant plus some isostructural activation barrier delta H over KT, natural log of 10. And this natural log of 10 just comes because we're writing this as a base 10 logarithm of the non-equilibrium viscosity. And this part here, this delta H over KT, note that this is an Arrhenius form of the viscosity. Note that it doesn't depend on the fictive temperature. It only depends on the temperature T. And this is the isostructural contribution, meaning if the fictive temperature is constant, then the structure of the glass is not changing. So if you have a constant structure, an isostructural system, that means a constant TF, but just changing the temperature, because it's frozen into that local environment, it has an Arrhenius dependence of the viscosity. So this term here corresponds to when you've cooled the glassy state low enough that you've entered the Arrhenius regime. And the slope, therefore, is given by this delta H here, this activation enthalpy for the isostructural contribution. So this term comes when you're changing temperature for a fixed fictive temperature. Now, the next term here is the thermal history dependence of the viscosity. And this is a bit more complicated here. It depends on, this is a constant here, and then it depends on the glass transition temperature, the fragility, and the fictive temperature. But note in the second part of the equation here that the temperature itself does not appear. In other words, this second term considers that the fictive temperature is changing, the TF appears in this part, but the T itself is constant. And so the two parts of this equation are, the first part is if you're changing temperature for a fixed fictive temperature, and the second part is if you're changing the fictive temperature for a fixed temperature. So this is telling you how much the viscosity is changing if you change the structure of the glass. So if you're changing the fictive temperature. And going back to the plot here, where this comes in is if you draw a vertical line through this plot, the vertical line corresponds to a constant temperature, but going from the green curve here to the red curve, what we're doing is changing the fictive temperature. So if you draw that vertical line here, that second part of the equation tells you how much the viscosity is changing by simply changing the fictive temperature. So how well does this map equation actually work? On the left here, this shows the viscosity of eagle XG glass as a function of time for isothermal holds at different temperatures. So this is taking eagle XG glass and holding it isothermally at either 600 degrees C, 650, or 675 degrees C. The experimentally measured viscosity using the beam bending technique is given by the black curves, and then the modeled viscosity is given by the dashed red line. So you can see that it has a very good agreement between the model and experiment. What you'll also notice is that the viscosity is increasing over time. It's increasing by oftentimes an order of magnitude or more over time, which is a huge change. And the reason is that over time, the glass is slowly approaching the supercooled liquid line. So if you were to take the glass, say here, and just hold it at this temperature, over time, it is relaxing towards equilibrium. So it's relaxing towards this equilibrium supercooled liquid state, which means that the viscosity over time is increasing, and it's increasing by orders of magnitude. And that is exactly what the model predicts, and that is exactly what is observed in experiment. If we try it out on another glass composition that has a higher glass transition temperature, this is called Corning jade glass. again with three different isothermal holds, but shifted up to higher temperatures, 700, 735, and 758 degrees C. Again, during those isothermal holds, the viscosity is increasing by a significant amount. And again, there is excellent agreement between the model and the experiment. We see that also for selenium. So this is a chalcogenide glass. This has, in this case, calculated viscosities here based on energy landscape simulations given by the black dots. And then the model results are given by the red dashed line here. So this is now as a function of fictive temperature, where you can see that the viscosity is changing by over 12 orders of magnitude with respect to fictive temperature. So it's a huge variation, and the model is able to capture that. If you take the Eagle XG results and instead of plotting them as a function of time, plot them as a function of fictive temperature, it looks like this on the right here. These are the three different isothermal holds at 600, 650, and 675 degrees C, now plotted as a function of fictive temperature. And you can see here that as you have a lower temperature, of course, the viscosity goes up at lower temperatures, but also over time, the system is relaxing from a high fictive temperature down to a lower fictive temperature. That is also causing the viscosity to increase. Now, one of the nice things about this map equation is that the parameters of the non-equilibrium viscosity all connect back to the parameters of the equilibrium liquid viscosity, the TG, the fragility index. And this enables a parameter-free prediction of non-equilibrium viscosity. So if you know the glass transition temperature and you know the fragility, that's really all you need in order to predict what the non-equilibrium viscosity would be like. This is an example of parameter-free predictions of non-equilibrium viscosity. The model results here in red for this particular high-performance display glass, and then the empirical results from an experiment shown in black. And again, there's excellent agreement for these isothermal holds at all four temperatures. Going to a somewhat lower temperature glass, Gorilla Glass, on the right, again, excellent agreement without any free parameters. So just putting in the glass transition temperature and the fragility of Gorilla Glass, you immediately get really good predictions of this non-equilibrium viscosity. Now, as I noted, one of the key parameters that appears in the non-equilibrium viscosity equation is the liquid fragility. And fragility, as defined by Angel, is a liquid state property, not a glassy state property. Nevertheless, the liquid fragility has a big impact on the non-equilibrium viscosity of the glassy state. And you can see this with this volume temperature diagram on the left. The dashed line here is the metastable supercooled liquid line for this selenium system. And what I've done here is to take selenium, which has a fragility of 49.65, and then make some hypothetical glass forming systems that have the same glass transition temperature as selenium, the same supercooled liquid line, but just changing the fragility independent of everything else. And when I do that, I get this less fragile system here in the blue curve and a more fragile system in the green curve. They all have the same glass transition temperature. They all have the same supercooled liquid line. But what you see is that the more fragile system has a much sharper glass transition. It has a lower viscosity at temperatures above TG, which enables it to stay in equilibrium for longer. But then, since the viscosity curve is so steep as you go through the glass transition, there's a much more sudden glass transition process, a more sudden freezing in of the supercooled liquid structure into the glassy state. And therefore, that gives us much sharper glass transition shown here in green. On the other hand, if you go to a lower fragility system, like the blue curve here, you see that since the viscosity curve is much more shallow, it's a more gradual glass transition. It's spread out over a wider temperature range. And this fragility has a direct impact on the viscosity as well. On the right-hand plot, you'll see they all have the same glass transition temperature, 10 to the 12 Pascal seconds. This is all the same TG, but the slopes here are different because the fragilities are different. And that ends up being very different viscosities in the non-equilibrium glassy state, where the more fragile system has a higher activation barrier, and therefore a much steeper slope here and a greater viscosity, even into the non-equilibrium state compared to the less fragile system. And it's the steeper slope here that leads to the much sharper glass transition process. And you can see this here on the left plot. This shows the fictive temperature as a function of the logarithm of cooling rate. The more fragile system, because of its steeper slope, is able to access a much narrower range of fictive temperatures because of that sharper glass transition. If you just take the same coverage of cooling rates, but have a less fragile system, shown here in blue, this covers a much wider range of fictive temperatures because of that shallower slope. And on the right-hand plot here, this shows the logarithm of viscosity for these three systems as a function of fictive temperature, where you can see that the more fragile system at low temperatures, this is at 212 Kelvin, that at these lower temperatures below the glass transition, the viscosity of the higher fragility system is actually much higher compared to the viscosity of the lower fragility system. Now, coming full circle back to the beginning of the lecture, I introduced this lecture with this urban legend of cathedral glass. And one of the interesting things is that in the earlier work from Zanotto and Gupta and Zanotto, they were using modern glasses and the state-of-the-art theory from back then to be able to estimate the viscosity of cathedral glass at room temperature. And so we wanted to revisit this problem using actual measurements and actual cathedral glasses. So we actually got the composition of Westminster Abbey cathedral glass. Rather than taking a piece from the Abbey, we made our own Westminster Abbey glass using their recipe. We made predictions of the non-equilibrium viscosity based on its glass transition temperature and fragility. And the model predictions here are shown in red. This shows the log viscosity versus temperature. We had a very patient measurement of viscosity here. This is the equilibrium viscosity in black, and then the measured viscosity of the non-equilibrium glassy state as the blue point shown here around close to 10 to the 18 Pascal seconds. So this measurement took a very long time. And you can see excellent agreement here between the measured result and the model predicted result. And if we plot this on the same plot as Gupta and Zanotto study, this is the log viscosity versus TG over T. Gupta and Zanotto were using modern soda lime silicate glass, which has a different composition compared to the medieval glass. They were using kind of the older theory, which was just a pure Arrhenius behavior here, not accounting for the continuous glass transition, which is shown by the curvature in the black line of our study. And they were using results that were obtained and published in literature using the state-of-the-art experimental techniques back then. And of course, we have much more precise measurements since then. So Gupta and Zanotto had predicted a viscosity of 10 to the 41.3 Pascal seconds at room temperature. Recall this was like 9 orders of magnitude lower than Zanotto's original prediction. However, with our study, we were actually showing significantly lower viscosity of the real medieval glass using the more advanced theory and experiments. It was 10 to the 24.6 Pascal seconds. So about 16 orders of magnitude faster flow. That's an enormous difference compared to the prediction from Gupta and Zanotto. However, it is still much too high viscosity to observe the viscous flow behavior on the time scale of hundreds of years. The other thing that we did was to actually do the fluid flow simulations to see how much this would flow under the force of gravity with a viscosity that is either 10 to the 24.6, which was shown with kind of an average guess at what the fictive temperature is, but we also considered a range of possible fictive temperatures here, calculated the surface velocity in blue, and the qualitative result is the same as what Gupta and Sonoda published, that the flow is too slow to actually observe. In fact, this viscosity would correspond to about 1 nanometers worth of flow over a billion years. So it's still much too slow to occur. But again, it points to the importance of accounting for the full thermal history and considering the non-equilibrium viscosity of glass. So to conclude, the non-equilibrium viscosity of glass scales exponentially with fictive temperature. Viscosity can change by orders of magnitude as a result of its thermal history and relaxation processes, and fragility is one of the key parameters governing the non-equilibrium viscosity of glass. So thank you very much for listening, and I will see you next time.